All right, guys, questions over the homework. All right, guys. All right, guys, so what we're doing today is continuing solving. We're continuing our chapter or section over solving exponentials and logarithmics. So we're continuing solving exponentials and logarithmics. Now, as we solved this on Thursday, we got the bases to be the same and set the exponents equal to each other. Now, if we look at 7, we can rewrite it as 2 to a power. That would be nice. Now, 2 to the first is 2, 2 to the second is 4, 2 to the third is. So is there any way that we could rewrite 7 as 2 to a power? No. At least we can't use the one-to-one property. But we can still solve this using logarithms. Now, the first step in solving these logarithmic or exponential equation is really to get one term on either side of the equal sign, or one term on either side. We want a single term on either side before we start applying any logarithm or exponent or base to both sides. The second is to get the variable or variables out of the power, out of the exponent, or log. We need to get the variable out of the exponent or the log so that we can be able to solve it. And the third step is to just solve. These are the three main steps, or the 3 steps we go through for solving these here. Now for this here, 2 to the x equals 7. To get that exponent out, we're going to apply a log to both sides. Now we could just take log, our common log base 10, and apply it to both sides. For this here specifically, I'm going to apply log base 2 to both sides. It's going to make it a little bit nicer, a little bit easier to solve. A lot of times when we solve these logarithms, we default to the natural log, ln, to solve here. Questions on this so far? One of our properties with logarithms that we had in chapter 6.5, our power property, says that if we have an exponent inside the log, we can move it to the front. So that tells us here that we have x times log base 2 of 2 equals log base 2 of 7. Now there's a reason I chose log base 2 to apply to both sides. And the reason is dealing with what the value of log base 2 of 2 is. Now if we go to math and we calculate log base 2 of 2, we see that its value is 1. And we've had this property before. Log base b of b is 1. When the base and the number inside the logarithm are the same, it's going to reduce to 1. Exactly. So the log base 2 of 2 is 1. Our 1 times x is just x. Guys, telling us that log base 2 of 7 is equal to x. X is equal to log base 2 of 7. Solve for x. Well, we have, yes? Yeah, so that is the answer. Now we can get the approximate answer because we can grab the calculator, go math, log base 2 of 7 is 2.807. Again, it is not going to be a whole number because when we tried to approximate 7 as 2 to a power, 2 to the second was too small, 2 to the third was too big. So it is going to be between 2 and 3, which it is, 2.807. And that's it. Questions on this here? On the homework and on the test, I will take either, really. All you got to give me is this, log base 2 of 7. Because the problem asked us to solve it. Log base 2 of 7 is the answer. That is the solution for this here. I will take that. Even on the test, I will take this. Because getting it to x equals log base 2 of 7, you did solve it. Going from that to the decimal approximation is not any extra solving. That's just seeing how well you can plug it in. Log base 2 of 7 solved. That's all I need. Questions on this here? Let's look at the next one. 3 to the x equals 8. One term on either side. So to get the variable out of the exponent, we can apply log to both sides. What can we say the base of this log is? We can use log base 3. We can move the exponent to the front, telling us that we have x times log base 3 of 3 equals log base 3 of 8. Log base 3 of 3 is 1. So this simplifies, leaving us with just x is equal to log base 3 of 8. And since x is by itself, we're done. More steps do get involved when we have variables on both sides in both exponents. Instead of having just 8, we have 8 to the x or 8 to the 3x. It gives us a few more steps, but the process will essentially be the same. It doesn't have to be, because we could use a different base if we want. So let's just say I left it as log. I didn't put a base at all, or write a base, so it's base 10. The property still holds true. We move the x over, telling us x log of 3, x log of 3 is equal to log of 8. Now, if we look at the calculator, log of 3 is not 1 anymore, and that's fine. So at this point here, to get x by itself, we're going to divide by log of 3. Log of 3 divided by log of 3 simplifies, telling us x is log of 8 over log of 3. And we can see here, see if that's different. Let's get the graphing calculator. There we go. Math. Log base 3 of 8 is this here. The one we just got was log of 8 divided by log of 3, which is the exact same thing because it's our change of base. So it does work. We can pick whatever log we want. Now, the reason we pick log base 3 is because on that left-hand side, log base 3 of 3 is 1. It makes things a little nicer. One less term to work with. You're welcome. And a lot of times with these here, if we're not doing the log base to match up, most will use log. Most of the time, instead of log, we'll use natural log. But questions on this here? Let's look at this one here. 7 to the 9x equals 15. One term, one term. So we can apply log to both sides. What base is going to make this nicer to work with? Having a base of 7. Because on the left-hand side, the 9x would move to the front, giving us 9x times log base 7 of 7 equals log base 7 of 15. Again, log base 7 of 7 is 1. Questions on how we got to this point here? We good with this here so far? Is x by itself. So the last thing we have to do in solving is to divide by 9, telling us that x is equal to log base 7 of 15 all over 9. Now, it might be very tempting that you might want to divide the 15 and 9. We cannot, because the 15 is stuck inside the log. It is possible to simplify it, but in order to do that, we have to approximate log base 7 of 15 first and take that decimal and divide it by 9. But we can leave it as this here. Questions on this here? Questions on anything we've done so far? We're ready for the next one. 5 to the 3x plus 7 equals 311. One term on either side. Even though we do have multiple terms in the exponent, that's fine. It's just one term, our 5. What base could we use for this here? 5. Because on the left-hand side, our exponent, even though it is two terms, the whole expression 3x plus 7 is going to move to the front, telling us that we're going to multiply it. Our 3 plus 7 is still being multiplied by our log base 5 of 5. All right, let's focus in. Which is equal to log base 5 of 311. Now again, the reason we chose 5, log base 5, is because this log base 5 of 5 is 1, and 1 times our 3x plus 7 is 3x plus 7. Now we just need to solve for x. So the first thing we can do is subtract 7 from both sides. Tells us that 3x is equal to what? Log base 5 of 311 minus 7. Because again, that 311 is stuck inside the log. We can't subtract 7 from it. The only way we could subtract 7 is if we get the decimal approximation. We'll leave it as this here. Last thing we have to do is what? Divide both sides by 3, telling us that x is equal to log base 5 of 311 minus 7 all over 3. And again, we leave it as this here because log base 5 of 311 is not a nice decimal number. It's an approximation. We have to approximate it because it's a non-repeating, non-terminating decimal. It's irrational. I mean, there could be some logs. There are some logs where the number, the value works out to be a nice number. Not always, but sometimes it does. And if it does, we can reduce it. We can work with that. Questions on this here? Do we feel comfortable with these here? Do we need to see another one? Because if you work this out, it should be log base 7 of 312 minus 3 divided by 5 is what we should get. But if we do feel comfortable with these here, let's look at this one. 4e to the negative 0.3x minus 7. Do we have one term on either side? Well, we have 13 on one side, yes? On the other side, we have the 4e, and we also have the minus 7. So before we can apply logs to it to get that variable out of the exponent, we need to reduce the left side to a single term. What can we do first? we can add 7, because our negative 7 plus 7 would reduce, leaving us with 4e to the negative 0.3. X is equal to, guys, what's up here? 20. Well, what else can we do? We can divide both sides by 4. Because our 4 divided by 4 will leave us with e to the negative 0.3x is equal to 5. Because we just want that term with the variable and the exponent by itself. One term on either side. Questions on any of this here? Well, now we can apply our log to both sides, yes? What log had a base of e? ln, it's our natural log. Natural log was the one that had the base of e. Because we could write log base e, but log base e is our natural log. And the properties of natural logs are the same as our logs. So we can move the exponent to the front. And like I said, we have negative 0.3x times the natural log of e is equal to the natural log of 5. Well, what is the natural log of e? It is 1. Natural log of e is 1. So this here reduces to 1, leaving us with negative 0.3x is equal to the natural log of 5. So this is essentially the same thing as what we were doing. We just had to get e by itself. We could have done it with another numbers. It looks a little funny, but it is possible. Last thing we have to do is divide by negative 0.3, telling us x is equal to the natural log of 5 divided by negative 0.3. Now again, we could plug these into the calculator. Natural logs are a little bit nicer in the calculator because natural log of 5 divided by negative 0.3 gives us negative 0.5365. So again, natural log of 5 over negative 0.3 is our answer. Questions on this here? We ready for the next one? 3e to the x minus 4 equals 8. We need to get e by itself, so we're going to add 4 to both sides. Telling us 3e to the x is equal to 12. Then what can we do? Divide both sides by 3. Telling us e to the x is equal to 4. Now we do have one term on either side, and since the base is e, we can apply the natural log to both sides. Now the natural log of e to the x, we move the x out front, giving us, well, x times the natural log of e, natural log of 4. Well, the natural log of e is still 1. So x is equal to the natural log of 4. Questions on this here? Are you ready for the next one? Do we feel comfortable with these here? Okay. Now these last three are a little different in that this time we're starting with a logarithm. Now we use logs to help us solve exponentials. So we're going to use exponentials as those bases to solve logarithmic equations. Now we had before b to the log base b of x is x. because when we put a base or put a log in the exponent and its base and the base of the log are the same, they simplify out. So if we look at this equation here, log base 2 of 5x minus 17 equals 3. Well, if I put our log base 2 of 5x minus 17 to the base of 2, 2 to the log base 2, well, this 2 and log base 2 are going to cancel, leaving us with 5x minus 17. But I can't do that to just one side. We also have to do it to the other. So on the other side, we have 2 to the third power. Does 2 to the third reduce nicely? 2 to the third is 8. We didn't do that with any of the logarithms because pretty much all the logarithms did not reduce nicely. This one does. So we can reduce it. Now we just need to solve for x. So we can add 17. Minus 5x is equal to 25. And then we would divide by 5, telling us x is 5. And that's it. Now we do have to be careful with logarithms because what's inside the logarithm, that 5x minus 17 cannot be 0 or negative. Because if what's inside the logarithm is 0 or negative, that's not going to work. That solution will not work. So any value of x that would make 5x minus 17 be 0 or negative, we have to throw out. And we could check this here and see if that happens. Log base 2 of 5 times 5 minus 17. Well, 5 times 5 is 25. And 25 minus 17 is 8. Log base 2 of 8 is indeed 3. So that does work because we're not having to take a log of a negative or 0. Questions on this here? All right. Log base 3 of 10x minus 9 equals 4. What base do we need to put both sides to? 3. Now we can go straight to doing this here because there is indeed one term on both sides. The log is a single term. We have a single log equals a number. Now here, 3 to the log base 3. This will cancel, leaving us with 10x minus 9 is equal to 81. 3 to the fourth power is 81. Next thing we can do is add 9, telling us 10x is equal to 90. Last but not least, we can divide by 10, telling us x is equal to 9. We could also do these with natural logs. It's just we would put both sides to the base of e. Questions on any of this here? Here, let's switch this up. Let's say ln of x minus 6 is equal to 5. Because if we used ln instead of log base 2, here we would put both sides to the base of e. Not using that. And here, e and the ln would cancel, telling us x minus 6 is equal to e to the 5th. Is e to the 5th a nice number? We can check and see. Second ln 5 is, no, e is irrational. E is a non-repeating, non-terminating decimal, so we'll leave it as e to the 5th. Add 6, telling us x is equal to e to the fifth plus 6. So it still works with natural logs. We just end up with e instead of a number to a power. Questions on this here? That is it.